We hope that in 15 to 20 years we will be able to develop universal quantum computers that can be used to solve a vast number of problems such as cryptanalysis, weather forecasting, drug design, as well as explore some complex problems in physics, chemistry, and biology.
After more than 20 years of research, the team succeeded in building the GBS and used it to provide a highly efficient way of demonstrating quantum computational speedup in solving some well-defined tasks.
Is important because Jian-Wei Pan and his colleagues demonstrate that quantum supremacy is also possible with quantum computers based on photons, on particles of light.
The breakthrough means China is becoming a trailblazer in the quantum computing field, laying a foundation for large-scale quantum simulators. 张悦，上海 Live。
你现在调3，关于这种的话，你能够看见的。一个微，但是我们那个是可以调的嘛？是有些地方你把它给反出来是吧？对，这要小很多了。
我如果把这个黑板拿掉，它打到我身上。
只要眼睛不打，因为眼睛而且如果明天这么讲的话，我们这么出来，我现在把这个出来，看它多微观，我把它分成13亿，可以把13亿做。
这样玻璃做出来有点微观的。太强了。哦，那个里面其实就是一个一个的。对。我知道，但1秒钟可以出来很多，但是那个就是用那个哪儿用那个光亮的话，它也不像那个原理。
相当于就是我一个光子，如果我能来操纵它的3个自由度的话呢，我就可以当做3个光子用。控制多个自由度呢，是一个我能进一步来提升我可以来操控的，就是有效的光量子比特数目的另外一个非常有效的途径。所以呢，我们是多条路径同时来探索，怎么样来达到非常高数目的这样一个纠缠比特的数目。
我们把这对在这个。
下一步的计划呢，就是说我们要来超越我们人类历史上第一台，比如说集成电路的这个经典的计算机，然后呢来超越我们现在商用的最快的这个计算机，然后最后一步呢来超越我们的超级计算机，这是我们的一个基本的一个计划。量子计算机呢，它是利用量子力学的原理。量子力学呢，它可以允许一个物体啊，同时处于多种状态。那么，比如说0和1同时存在，它可以做一个原理上的叫做变形计算，就是很多个任务呢可以一起来把它完成。因此呢，它就有了这样一种超越经典计算机的这样一个计算能力。
那么，在我们的这个量子计算里面啊，第一个里程碑性的目标呢，就是要来展示啊量子计算的优越性。我们在这个高斯波折采样这个实验当中呢，构建了一个量子计算的原型机，可以比目前最快的超算呢能够快10的14次方倍，就相当于我这里算1分钟的东西呢，用傅约号拿来算的话呢，要算1亿年，它才能把这个事情呢给算完。这就是叫做量子优越性，就是我总算可以演示某个功能比传统的超级计算机算得好了。这样的话呢，我们就可以进一步的去寻找各种各样的应用，希望能够通过呢15年到20年的努力呢，能够研制出呢通用的量子计算机。这样的话呢，它就可以来解决呢很多非常广泛的问题了，比如包括密码分析啊、气象预报啊、药物设计啊，然后来探索物理学或者化学、生物学里面的一些复杂的问题。
I think it's a remarkable achievement. It's a milestone in the development of these intermediate scale quantum computers.
Is important because Jian-Wei Pan and his colleagues demonstrate that quantum supremacy is also possible with quantum computers based on photons, on particles of light.
Quantum computers use the natural world to produce machines with staggeringly powerful processing potential.
I think it's going to be the most important computing technology of this century, which we are really just about 1/5 into.
We could use quantum computers to simulate molecules to build new drugs and new materials, and to solve problems plaguing physicists for decades. Wall Street could use them to optimize portfolios, simulate economic forecasts, and for complex risk analysis. Quantum computing could also help scientists speed up discoveries in adjacent fields like machine learning and artificial intelligence. Amazon, Google, IBM, and Microsoft, plus a host of smaller companies such as Rigetti and D-Wave, are all betting big on quantum.
If you were a billionaire, how many of your billions would you give over for an extra 10 years of life?
Is quantum truly the next big thing in computing? Or is it destined to become something more like nuclear fusion, destined to always be the technology of the future, never the present? You've probably heard or read this explanation of how a quantum computer works. Regular or classical computers run on bits. Bits can either be a 1 or a 0. Quantum computers, on the other hand, run on quantum bits, or qubits. Qubits can be either 1 or 0, or both, or a combination of the two at the same time.
Quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
The goal for quantum computers is to make sure the amplitudes leading to wrong answers cancel each other out.
You have a chip the size of an ordinary computer chip, and you have little coils of wire in the chip, which are actually quite enormous by the standards of qubits. They're nearly big enough to see with the naked eye. Okay, but you can have two different quantum states of current that are flowing through these coils that correspond to a 0 or a 1. And of course, you can also have superpositions of the two. Now, the coils can interact with each other via something called Josephson junctions. Okay, so they're laid out in roughly a rectangular array, and the nearby ones can talk to each other and thereby, generate these very complicated states, what we call entangled states, which is one of the essentials of quantum computing. And the way that the qubits interact with each other is fully programmable. Okay, so you can send electrical signals to the chip to say which qubits should interact with each other ones at which time. Now, in order for this to work, the whole chip is placed in a dilution refrigerator that's the size of a closet, roughly, and that cools it to about 1/100 of a degree above absolute zero. That's where you get the superconductivity that allows these bits to briefly behave as qubits.
This qubit around this one over here will feel it, and if you do that in a controlled way, you can move lots and lots of information around within your quantum